Let's look at maxima and minima of a function of two variables. So let's say z is equal to f of x comma y. So a function of two variables. Let z naught be the value of f of x comma y at x naught y naught. So the question is, when will z is equal to f of x comma y have a maximum at x naught y naught? Now that would happen if f of x comma y is less than f of x naught y naught nearby to x naught y naught. So if we look at this something like this, so here on both the sides it will be lesser. So at every other point except at x naught y naught it would be less. Okay, so similarly, when will z is equal to f of x comma y have a minimum at x naught y naught? If f of x comma y is greater than f of x naught y naught nearby to x naught y naught. So which means something like this. So this is x naught y naught. At every other point it will be greater. Now maximum and minimum values of f of x comma y are called extremum values of the function. So now let's say x is equal to x naught plus delta x, that is nearby point near to x naught, and y is equal to y naught plus delta y. So let's say at every other point nearby to x naught y naught is less than f of x naught to y naught. Now this can be written as f of x naught plus delta x comma y naught plus delta y, and we bring this to the other side, so minus f of x naught y naught, and this would be less than 0. In short, we can write, now this is the value at a point nearby to x naught y naught, and this is the value at x naught y naught. So we can say delta f would be less than 0. So delta f is nothing but the value at delta x delta y. So basically this implies that f of x comma y is maximum at x equal to x naught and y is equal to y naught if delta f is less than 0. Now based on the same set of arguments, similarly f of x comma y is minimum at x equal to x naught and y is equal to y naught if delta f is greater than 0. Now based on this, let's look at a theorem. If the function f of x comma y attains extremum at x equal to x naught and y is equal to y naught, then each first order partial derivative fx, fy either would vanish or would not exist. So let's see, z is equal to f of x comma y, a function of two variables. Let's keep y constant at y equal to y naught. So f of x comma y naught is going to be a function of single variable, that is x. Then if f of x comma y naught has an extremum at x equal to x naught, then dou f by dou x would be equal to 0 or does not exist. So this is what it implies. Similarly, let's say x is a constant at x equal to x naught. So which means f of x naught comma y is a function of single variable y. Then if f of x naught comma y has an extremum at y is equal to y naught, implies that dou f by dou y is equal to 0 or does not exist. So a point x naught y naught at which fx equal to 0 and fy equal to 0, that means partial derivative with respect to x, and here it is partial derivative with respect to y, or they don't exist, is called critical point or stationary point. Okay, now let's look at sufficient condition for an extremum. How do we decide whether a particular point is an extremum? So z is equal to f of x comma y is a function of two variables. Let z have continuous partial derivatives up to and inclusive of order 3 in certain domain, that means for certain values of x, containing the point x naught y naught. Now let x naught y naught be the critical point, that means it is either a maximum or a minimum. Critical point of z, so that fx x naught y naught is equal to 0, fy x naught y naught is equal to 0. Then f of x comma y has a maximum at x naught y naught f the second partial derivative with respect to x times second partial derivative with respect to y minus this is partial derivative with respect to x and y square is greater than 0, and second derivative with respect second partial derivative with respect to x is less than 0 at x naught y naught. So for that critical point to be a maximum, this should be greater than 0 and this should be less than 0. Okay, now f of x comma y has a minimum at x naught y naught if fxx yy fyy times minus f square xy, this again has to be 0, and fxx second partial derivative with respect to x is greater than 0 at x naught y naught. So here this condition remains the same. The second partial derivative with respect to x is less than 0 means maximum, greater than 0 means minimum. Okay, f of x comma y has no extremum at x naught y naught if fxx times fyy minus f square xy is less than 0 at x naught y naught. And fourth, if fxx times fyy minus f square xy is equal to 0 at x naught y naught, then we have to do some further study. Okay, so here the critical thing is we have to evaluate this first, right? If it is greater than 0, then yes, there is an extremum. If it is less than 0, no extremum. If it is equal to 0, further study. Now, here, now if it is yes, then we have to look for and fxx equal is, let's say here, less than 0. Less than 0. That means it is maximum. It is minimum. Yes. Okay. Now let's actually solve one or two problems to understand how this all applies. So let us say f of x comma y is equal to 2x square minus xy plus y square plus 7x. Now what we have to figure out is the critical points. So straightforward, partial derivative with respect to x would give us 4x minus y plus 7. Partial derivative with respect to y would give us minus x plus 2y. And partial derivative with respect to x and y will give us, we can take this and find the partial derivative with respect to y, or we can take this and do the partial derivative with respect to y. So this would be, let's take the first one. So minus 1. Let's do this. F of, first of all, we have to make sure that this is equal to 0. This is equal to 0. Yes. So that we can evaluate the x naught y naught. So let's solve this. We have simultaneous linear equations. So 4x minus y plus 7 equal to 0. And we have minus x plus 2y equal to 0. So 2y equal to x. Y is equal to x by 2. So now that we can substitute it here. Minus x by 2 plus 7 equal to 0. 8x minus x plus 14 equal to 0. 7x equal to minus 14. X equal to minus 2. This x equal to minus 2, let's put it here. So minus 2 by 2, which is minus 1. So therefore minus 2 comma minus 1 is the critical point. Now the only thing we have to figure out is whether it is a maximum or a minimum. Now fxx would be what? We have already figured out fx. So let's take that and partially differentiate with respect to x. So here we get 4. Here we get 2. Okay. So 4 fyy is equal to 2 and fxy is equal to minus 1. Now fxx times fyy minus f square xy. Let's evaluate this. 4 times 2 minus 1 square. So this becomes 8 minus 1, which is 7. And this is greater than 0. So use this decision tree. It is greater than 0. Is fx second partial derivative with respect to x? Is it less than 0? It is greater than 0. So which means fxx is greater than 0. This is greater than 0. Both are greater than 0. Therefore, at minus 2 comma minus 1, f of x comma y has a, this is greater than 0. Here it is yes. Here it is no. So another way to remember is, if they should be both be greater than 0 for it to be minimum. Okay, let's do one more problem. Show that a rectangular solid of maximum volume, which can be inscribed in a sphere of a is a cube. That means we have a rectangular solid. Within that, we are actually creating a sphere. Okay, what this means is that we have a rectangular solid, and inside that we are creating a sphere. Right? Now, what we have to see is that the volume of this sphere is going to be highest only if this rectangular solid is a cube. That means all the sides are equal. That is what we have to show. Okay, so let's say let sides of rectangular solid x, y and z. Now see, if you take it as x, y and z and keep going forward, you might realize that you end up with tricky calculations. So let's make it as 2x, 2y, 2z. Okay, now let a be the radius of the sphere. Now the volume would be what? Volume of the solid, let's say v is equal to length into breadth into height. Yes, these are rectangular solid. So 2x times 2y times 2z, which is equal to 8xyz. Now the equation of the sphere is what? Equation of sphere, S-P-H-E-R-E, sphere is x square plus y square plus z square is equal to radius square. Now somehow we have to mix these two up. Yes, solving for both the equation means we have to mix them up, right? So let's take the square of this. You will see what I mean. V square is equal to 8 square x square y square z square. Now let's take one of these and do the substitution. Yes, so 8 square x square y square and z square would be what? These two, let's take it to the other side. So a square minus x square minus y square. Yes, and let us say this is the function for which we have to find the critical point, the maximum. Okay, so our function is v square is equal to 64 x square y square a square, 64 x4 y square minus 64 x square y4. 64 is common, so let's take it out. X square y square a square minus x4 y square minus x square y4. Now that we have it like this, let's find the partial derivative with respect to x, dou f by dou x. This will give us 64 as it is with respect to x. So 2x y square a square minus 4x cube y square minus 2xy4. Now dou f by dou y, partial derivative with respect to y. So 64 2x square y square 2y a square minus 2yx4 minus 4y cube x square. Yes. So at the critical points, dou f by dou x would be 0, dou f by dou y will be equal to 0. So which means this would be equal to 0 and this will be equal to 0. So let's solve these two equations. So 64 will disappear. If we take it to the other side, 64 would disappear. And let's take commonality out. So what do we have? 2 is common to all of them, x is common to all of them, y square is common to all of them. So we have 2xy square common out. So a square minus 2x square minus 2xy, no, 2x is already gone out. So y square equal to 0. This is dou f by dou x. Now this also disappears when we take it to the other side. So a square minus 2x square minus y square equal to 0. Or a square is equal to 2x square plus y square. Now let's take the other equation, this one, dou f by dou y, and equate it to 0. So this is what? 2x square y a square. No, let's take common out in one step itself. Here 2x square x square y. Okay, 2x square y we can take it out, and we are left with a square minus x square minus 2y square equal to 0. Now this disappears when we take it to the other side. A square minus x square minus 2y square equal to 0, or a square is equal to x square minus 2y square plus 2y square. Now LHS is equal, so therefore 2x square plus y square is equal to x square plus 2y square. No, x square, let's rearrange them. So 2x square minus x square is x square, 2y square minus y square is y square. Yes. So which means a square is equal to 2y square plus y square. We can do that. We can do the substitution. Instead of y square we can put it as x square, or x square we can put it as y square. Okay, so this becomes 3y square, square root of 3y square, or 3 square root of 3y. So which means y is equal to a by square root of 3. Now since x and y are equal, x is equal to a by root 3. We have the setup x square plus y square plus z square is equal to a square. Let's do the substitutions. A square by 3 plus a square by 3 plus z square is equal to a square. So 2a square by 3 plus z square is equal to a square. 2a square plus 3z square is equal to 3a square. Now let's take this to the other side. So 3z square is equal to a square. Z square is equal to a square by 3, or z is equal to a by root 3. So As we see, x equal to y equal to z is equal to a by root 3, which means what? This implies that the rectangular solid is a cube, since all its sides are equal. So that is maxima minima. Okay, let's very quickly summarize. So f fxx evaluate this, fyy evaluate this, fxy evaluate this. Take the square of this. Evaluate this expression. If it is greater than 0, then you have to do one more check. If this is less than 0, then it is maximum. If it is greater than 0, then it is minimum. Now, if fxx fyy minus f square xy is less than 0, then no extremum. Now, if xx fyy minus f square xy is equal to 0, further study. That means you have to do something else. That's it for today. Bye for now.